This is a recording of the Chapter 2, Section 3A worksheet solutions. We're going to start with just going over problems 2, 4, 6, 8, and 10 here. I already have it written out, so you may need to pause the recording as we go. But in each one of these cases, I'm going to explain the solutions as we go through. First of all, anytime we're dealing with a rational situation, the worksheet is asking you to identify the discontinuity and say the type of the discontinuity. And then I also want you to list the interval over which this function is continuous. Okay? So on this first one, anytime we're dealing with a rational situation, we always want to consider when the denominator equals 0. Hopefully it's factorable. We're going to run into a lot of factorable trinomials like this. X minus 1 times x minus 3. If you multiply that out, you get this. Two numbers multiply to be positive 3, add up to be negative 4. This creates two situations in which the denominator equals 0. X equals 1 and x equals 3. Neither of these factors cancel with a factor in the numerator. Therefore, they are not removable discontinuities. They are infinite discontinuities because they are asymptotes. This function, this rational function, is continuous from negative infinity to 1, in union with 1 to 3, in union with 3 to infinity. By not bracketing the 1, we are eliminating 1 from the interval of continuity. By not bracketing the 3, we are eliminating the 3 from the interval of continuity. Problem 4. This is an absolute value function. And again, you can look at this in your calculator. I'm not going to verify each one of these by pulling up the calculator and looking at it, but you certainly could do that. In problem number 4, this is an absolute value function. An absolute value function is continuous everywhere. Yes, it has a vertex, which is actually called a corner when x equals 1. When x equals 1, we get out 0, and there's a corner at the point 1, 0. But there is no discontinuity. There's none. This function is continuous from negative infinity to positive infinity. I'm only using interval notation on the continuous intervals, and that is typically how it would be expressed using interval notation. But it certainly wouldn't be incorrect if you said x is the element of all real numbers. Please do not use ARN. 6. Again, a cubic function. A cubic function is continuous everywhere. We can take the cube root of any number, positive or negative. So the cube root function is a sideways cubic. And again, you can look at it in your calculator. Yes, it's been shifted and it has some shrinkage going on here because of the 2. Okay? But the fact of the matter is, there are no discontinuities. It is continuous from negative infinity to positive infinity. And again, if you want to look at it in your graphing calculator. I don't know why they created so many in the book where it was continuous everywhere, but I will tell you both of these functions are going to have what we call differentiability issues in Chapter 3. So number 8 on this particular worksheet is probably the hardest to write. Okay? When we're dealing with a cotangent function, what we need to know about a cotangent function is that the cotangent function has an asymptote at 0, pi, 2 pi, 3 pi. So essentially it has a discontinuity at x equals pi n at every multiple of pi, where n is assumed to be any integer. You could also use z here instead of n. That really is the letter that represents the set of all integers. Our book tends to use n instead, but in upper level math, when you get into real analysis, those types of courses, they'll use z to represent any integer. Okay? These are all asymptotes, so they're all infinite discontinuities. And then really the best way to state when this function is continuous is to say all real numbers except when x equals pi n. It's probably the best way to write it. Okay? Problem number 10. It's important to know natural logs have vertical asymptotes. So we have a vertical asymptote at x equals -1, and asymptotes are called infinite discontinuities. This function is continuous from -1 to infinity, but we have a parentheses at -1, not a bracket. Okay? So really, this function is not continuous from -infinity to 1 if you were to state it as an interval. I just want you to state where that discontinuity occurs. Okay? So this is fine, right? This is fine, but please understand this function is not defined here. Some books would actually say this function is continuous everywhere because it's continuous over its domain. But I still want you to recognize these infinite discontinuities, these asymptotes, and be able to describe that as an infinite discontinuity. All right, now we're looking at some problems in which they give you this picture. This picture is provided for you on the worksheet. Part of the reason why I type up the worksheet is so all of this information is already right here for you. So we have this parabola, but only from -1 to 0. Then we have a line with a slope of 2 from 0 to 1. But then this point has been removed and placed down here. It's the point 1, 1. Then it's a negative sloped line. And then it is a horizontal line. So let's just start. Does f at -1 exist? Yes, right there. It's a filled in hole. F at -1 is 0. Does the limit as x approaches -1 from the right exist? Well, as I get closer and closer and closer to x equaling -1 from the right, the y value is getting closer and closer and closer to 0. So yes. Does the limit as x approach -1 from the right equal f at -1? Yes. They're both 0. Is f continuous at x equals -1? This is where some students find this to be a little bit difficult because the answer here is yes. That is the endpoint of the domain. It is the last value of x described in this domain. And since the right-hand limit equals the value of the function, since it's an endpoint, that is enough to say that this function is continuous at that endpoint. The justification is to say the limit as x approaches -1 from the right of this function equals f at -1. That is the definition of continuity at an endpoint. Much different than continuity at an interior point. Let's take a look. We're probably going to run into some of that. Problem 12. And I do have to keep going up and down here a little bit on this one. So does f at 1 exist? Yes. F at 1 is 1. That's the point right there. F at 1 is 1. So yes, it exists. Does the limit as x approach 1 exist? Yes. The limit as we approach 1 from the left is 2. The limit as we approach 1 from the right is 2. So the limit as x approaches 1 is 2 because the left-hand limit equals the right-hand limit. However, does the limit as x approach 1 of this function equal f at 1? No. F at 1 is 1, and the limit as x approaches 1 is 2. Since the value of the function does not equal the value of the limit, we have a removable discontinuity. Is f continuous at x equals 1? No. Because the limit as x approaches 1 of f of x does not equal f at 1. We have a removable discontinuity. 13. Is f defined at x equals 2? So now we're talking about 2. Is f defined at x equals 2? No, that's an open circle. Look here, it's not defined at 2. So the answer to that is no. Is f continuous at x equals 2? No. Does the limit exist at x equals 2? Does the limit as x approach 2 of f of x exist? Yeah, it's a removable discontinuity. The limit does exist. They didn't ask that question. The limit does exist. But they do ask is it continuous at x equals 2? And that answer is no. We have a removable discontinuity because the limit as x approaches 1 of f of x does not equal f at 1. 13. Is f defined at, oops, here it is. So the limit as x approaches 2 of f of x does not equal f at 2. That's what I meant to say. We have a removable discontinuity. Yes, the limit exists, but the limit does not equal the value of the function because the function is not defined at 2. So we have a removable discontinuity. Remember, removable discontinuities, just as a refresher, removable discontinuities can be removed and replaced somewhere else, or they can be removed and thrown away completely. This one has been removed and thrown away completely. This has been removed and placed somewhere else. Good. I replicated this here, so make it a little bit better. At what values of x is f continuous? Again, this gives some students some difficulty. Remember, we have a bracket on -1 because it is continuous at this left endpoint. To 0, it's certainly not continuous at 0. We have a jump discontinuity at 0, so that's been eliminated. 0 to 1, 1 to 2, 2 to 3. Notice it is not continuous at 3 because of this open circle here. What value should be assigned to f at 2 to make the extended function continuous at x equals 2? Well, if we make f at 2 equals 0, it will fill in this removable discontinuity. And then the left-hand limit will be 0, the right-hand limit will be 0, therefore the limit as x approaches 2 will be 0, and f at 2 equaling 0 would then make it continuous. It would fill in this removable discontinuity. What value should be assigned to f at 1 to make the new function continuous at x equals 1? Right now, f at 1 is 1. But if we make f at 1 equal 2, it would take the point from here and put it right here. It would fill in that removable discontinuity and make this continuous. Is it possible to extend f to be continuous at x equals 0? If so, what value should the extended function have there? If not, why not? The answer is no. We have a jump discontinuity. We cannot extend jump discontinuities. We can only extend removable discontinuities. Okay? Moving on to the next one. The only difference between that problem and these next few problems is that you have to draw the graph. So we have to be very good at piecewise functions. If we draw this particular function, start with the top will be the left piece. I'm not supposed to plug 2 into here, but I need to. 3 minus 2 is 1. That's why the left piece starts here. And then the slope is up 1, back 1, up 1, back 1, up 1, back 1. Here it is. I have an open circle. I'm not supposed to plug 2 into this function, but I need to. Am I going to take off right from this open circle, or is it going to jump up somewhere and take off? 1/2 of 2 is 1. 1 plus 1 is 2. It does not take off from this open circle. I have to create another open circle right here. And now the slope is up 1 over 2, up 1 over 2, up 1 over 2. So we have a discontinuity at x equals 2. It is a jump discontinuity because the limit as x approaches 2 from the left of f of x does not equal the limit as x approaches 2 from the right. The limit as x approaches 2 from the left of this function is 1, while the limit as x approaches 2 from the right of this function is 2. And as soon as the left-hand limit does not equal the right-hand limit, there is no limit. And you must have a limit before you can even consider continuity. 20. Let's draw this one. Okay, so for problem number 20, we're looking at this particular situation when we graph this piecewise function. Again, I am not supposed to plug 2 into this function, but I need to know where we're going to start. It's just going to be an open circle. It may get filled in, it may not. But when I plug 2 into here, 3 minus 2 is 1. So I have an open circle. I can plug points in, or I can just count the slope backwards. Up 1, back 1, up 1, back 1, up 1, back. Look at the y-intercept is 3. This has a y-intercept of 3. That is this line segment. Graphing this function from left to right means graphing this next. This says when x is 2, the y value is 2. So this point right here stays open and we graph this solid dot right here. Now I need to graph this last piece to know, is it going to take off from here and be a jump discontinuity, or is it going to take off from here and be a removable discontinuity? That's the difference. If I plug 2 in, a half of 2 is 1. It's taking off right from here. Except now the slope is up 1 over 2, up 1 over 2, up 1 over 2. So we have a discontinuity at x equals 2. This is a removable discontinuity because the left-hand limit equals the right-hand limit, so we have a limit. The limiting value is 1. But the limit as x approaches 2 of f of x does not equal f at 2. Because the limit as x approaches 2 is 1, and the value of the function at 2 is 2. If we wanted to make this piecewise function continuous, we could do that with one simple change. Instead of x equaling 2 producing 2, we would just change this number to a 1, and that would fill in the removable discontinuity from these 2 line segments. 21. Draw a graph of this. This is kind of a unique one, and it does present an interesting situation in that this is a rational function. It has a vertical asymptote at x equals 1, dot, 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 dot. It has a horizontal asymptote at y equals 0, dot, dot. If you plug 0 into this function, you get out -1. That's enough to know what's going on, that this graph is down here. It has approached the horizontal asymptote going this way. It has approached the vertical asymptote going this way. But then it stops being this rational function. It says when x is 1, now it's going to be defined by this cubic function. If I plug 1 into this cubic function, we get out 4. And I could plug 2 in, you get out a value. It's just going to be this cubic function taken off from here. So the limit as x approaches 1 from the left goes to -infinity, while the limit as x approaches 1 from the right goes to 4. The left-hand limit does not equal the right-hand limit, therefore there is no limit. As soon as you don't have a limit, you do not have continuity. There is a discontinuity at x equals 1. This is an infinite discontinuity because it doesn't jump and start again. Anytime it approaches an asymptote, we identify it as an infinite discontinuity. Notice again, the limit as x approaches 1 from the left is -infinity. The limit as x approaches 1 from the right is a +4. And since the left-hand limit does not equal the right-hand limit, therefore, this means therefore, the limit as x approaches 1 of f of x does not exist. And as soon as we don't have a limit, we cannot have continuity. I have seen a question on the AP test before that references, can you have a point on a vertical asymptote? Not very often, very, very rare. In order to have a point on a vertical asymptote, it has to be a piecewise defined function like this, where we have an asymptote from one side of the function, but now we have a solid point going. Okay? And it doesn't always have to be a piecewise. It could be an integer function. We've seen one that was an integer of x or over x type situation. Okay? 22. Draw a graph of this piecewise function. Identify any asymptote. I cannot plug 1 into here, but it's the first thing I'm going to start with because 1 minus 1 is 0. If I plug 0 in, I get 1 out. -1 in, I get 0 out. -2 is -3. -3 in here is -8. And I can graph this asymptote. As a matter of fact, I can even plug in values like 2. And if I plug 2 in, I get -3 out. X cannot equal 1 is defined by this, but the rest of the parabola is defined except at this open circle. And sometimes students will forget to graph this part. to the right of 1 is defined by this parabola. So it is this parabola just at this point. The parabola is not defined, does not define the point x being 1, y being 0. That's why I have this open circle. It is removable, whether they place a point somewhere else or not, unless they fill that value in. And they don't. They say when x equals 1, we're going to place that point right here. So I have a discontinuity x equals 1. It is a removable discontinuity. It's a removable discontinuity because the left-hand limit equals the right-hand limit. They both equal 0. Therefore, the limit as x approaches 1 of f of x is 0. We have a limit, but we still do not have continuity because the limit as x approaches 1 of this function does not equal f at 1. The limiting value is 0. The value of the function is 2. Therefore, f of x is not continuous at x equals 2. The limit exists, but it's not continuous. Removable discontinuities. The limit will exist, but it's not continuous because the point has been removed. If we wanted to make this function continuous, we would simply redefine x equals 1 as 0 instead, and that would fill in that removable discontinuity. 23. Now they provide the graph, and for each one, identify the discontinuity and state whether discontinuity is a removable discontinuity or a jump discontinuity. So we have a discontinuity at 0. Because the left-hand limit equals the right-hand limit, there is a limiting value, but f at 0 is 1. This point has been removed and placed up here. So it's a removable discontinuity. If we want to make this function continuous at x equals 0, we would simply take this point from here and put it here. Okay? We also have a discontinuity at 1 because the left-hand limit is 1 and the right-hand limit is 0. Since the left-hand limit does not equal the right-hand limit, we have a discontinuity. And this is a jump discontinuity. It has to jump down before it starts again. 24. Okay? Identify discontinuities. Some students want to say we have a discontinuity at 0. It's continuous. I can come here. I don't have to pick anything up. It's fine. We have a discontinuity at x equals 1. That's the first one from left to right. This is a jump discontinuity because the left-hand limit is 2 and the right-hand limit is 1. We do not have a limit. And as soon as you do not have a limit, you cannot have continuity. This is a jump discontinuity. Where x equals 2 is a removable discontinuity. As I approach 2 from the left, the y value approaches 1. As I approach 2 from the right, the y value is getting closer and closer to 1. Even though the value of the function at 2 is 2, we have a limit. But we don't have continuity because this point has been removed and placed up here. If we wanted to make this function continuous at x equals 2, we would have to take the point from here and place it in this hole, and then this function would be continuous at 2. Problem number 41. I love these questions. You are actually drawing your own functions. They're just describing what they want you to graph. Okay? The y value here, the y values do not matter. I did not have to give you a graph that was labeled at all. You could place it anywhere. Okay? The only thing that they say is that f at 3 exists, so I do have a closed circle at 3. But the limit as x approaches 3 does not exist. So that means as I approach 3 from the left, it cannot have the same value as I approach 3 from the right. This is one of several different graphs that you could have, right? A jump discontinuity. You could have had the right hand come to 3 and the left hand not come to 3. That would have been fine. There's a number of different ways that you could have graphed this. Same with 42. f at negative 2 exists. Put a point at negative 2 somewhere. The limit as x approaches negative 2 from the right equals f at negative 2. So now this time we have to make sure that as we approach from the right, we're going to connect to this value. Because it says the right-hand limit equals the value of the function at negative 2. But the limit as x approaches negative 2 of f of x does not exist. So as we approach negative 2 from the left, we could have went to infinity if we wanted to, or negative infinity. I just put an open circle there so that as we approach negative 2 from the left, okay, it's approaching a different value. So I created a jump discontinuity as opposed to an infinite discontinuity. 43. Sketch a possible graph for the function stated here. F at 4 exists. The limit as x approaches 4 exists, but f is not continuous. If the limit exists, the only thing that we can have is a removable discontinuity. So f at 4 exists. I put a point somewhere. When x is 4, I put a point somewhere. I put it having a y value of 4, but it didn't have to be a y value of 4. And it says that the limit as x approaches 4 exists, but it's not continuous. So the left-hand limit and the right-hand limit cannot come to this point. It would be continuous. I have to make sure that the left-hand limit equals the right-hand limit, but that the value of the function is some other value in order to graph this description. It's a removable discontinuity with the removed point displaced somewhere else. 44. Sketch a possible graph of a function f that has the stated properties. F of x is continuous for all x except at x equals 1, where f has a non-removable discontinuity. I decided to create an infinite discontinuity here. As I approach from the left, it goes to positive infinity. As I approach from the right, it goes to negative infinity. You could have created a jump discontinuity here as well, if you would have preferred. 48. Find a value a so that the function is continuous at x equals 2. Okay? This is the breaking point. When it stops being this line and it becomes this line, I want to make sure when this line stops, this line takes off right from where this line stops. What will be critical when these appear on the free response is you have to state your justification. Whenever you're talking about continuity of a piecewise situation, you're always going to state this. The limit as x approaches the x value at the breaking point, in this case 2, from the left of the function, has the equal the limit as x approaches 2 from the right of this function, has the equal f at 2. This is important. All of these have to be the same. That simply means when I plug 2 in for x into the top function, I get 4 plus 3 is 7. I can set that equal to when I plug 2 into x for the bottom. 2a plus 1. And then just solve for a. Subtract 1 from both sides of the equation. Divide both sides of the equation by 2. A equals 3. You could graph it, but you don't need to. But when this line stops and this one takes off from this line, it will take off from right when this point stopped. Okay? At x equals 2. It will be continuous. 50. Same type of situation, except now I have a parabola and a cubic function. I still have to state this. This is what will constitute 1 point on your test. Your justification for why you're plugging 1 in to the top and the bottom and setting them equal to each other. Because essentially we're taking the left-hand limit, setting it equal to the right-hand limit, and making sure then that the value at the f at 1 will be the same as these two. This is the definition of continuity. That the left-hand limit equals the right-hand limit, therefore we have a limit, and that the value of the function equals the value of the limit. In this case, the breaking point is 1. So the limit as x approaches 1 from the left of this function has to equal the limit as x approaches 1 from the right of this function, and it has to equal f at 1. This is important. If these two are equal, that just ensures that the limit exists. We have to set it equal to f at 1 to to justify continuity. But ultimately, we just plug 1 into the top equation, plug 1 into the bottom equation. 1 plus 1 is 2 plus a. 1 cubed is 1. Subtract 2 and a equals negative 1. The solution is the easy part. The justification using correct mathematical notation on an AP test, that is the more difficult part. This is why we have to write this every time that we're justifying continuity. Left-hand limit equals right-hand limit equals the value of the function. 55. This kind of got cut off here. I'll read it to you. You should be able to see it on your paper. But for 55, it says, it is possible to extend the definition of a function f at a jump discontinuity x equals a, for that f is continuous at x equals a. So in other words, can you create a continuous extension at a jump discontinuity? That is false. Only removable discontinuities can be extended. That's your justification. 56. On which of the following intervals is this function not continuous? Well, it's not continuous when it's not defined, right? This function is defined from when x is greater than or equal to, when x is greater than 0. Okay? So this function is defined when x is greater than 0. It can't equal 0 or we'd have 0 in the denominator. This wants to know which of the following intervals is this function not defined. Okay? This is kind of a confusing problem because a lot of students look at this and say, oh, wait a minute, this is, well, look at it. It is continuous from 0 to infinity. That is the domain. It is continuous from 0 to infinity. It is continuous from 0 to 2 because that's in the domain. It is continuous from 1 to 2. It's continuous from 1 to infinity, 1 inclusive. It is not continuous on this interval because it is not continuous at x equals 0. We have an infinite discontinuity at 0, so we cannot have this bracket here. So this can be a little bit confusing. We're selecting which one of these intervals describes an interval that is not continuous for this function. And B is a not continuous interval because it's not continuous at 0. Because 0 makes the value of x equals 0 makes the denominator equal 0. 57. Which of the following points is not a point of discontinuity? Okay? X equals negative 1, x equals negative 1/2. The function's not even defined there. It's not defined here. It's not defined at 0. It's not defined at 1/2. At x equals 1, that is the endpoint of this domain. And this function is continuous at that endpoint because it is the left-hand limit of the domain. The domain in this function is x is greater than or equal to 1. And if I plug 1 in, I get 0 out. The right-hand limit equals the value of the function, and it's the endpoint of the domain. Therefore, this function is continuous at x equals 1 because it meets the criteria for being continuous at the endpoint of a domain. Very technical questions, 56 and 57. Great questions. 58. Multiple choice. First thing we have to do on this multiple choice is graph this particular situation. I'm not supposed to plug 0 into here, but I have to. 2 times 0 is 0, so I put an open circle here because there's no equal to. The slope is up 2 over 1, but I have an open circle here as well because there is no equal to underneath this inequality symbol. Then, working from left to right, this function says when x equals 1, the y value is 1, so it does not fill in that hole. We have this point right here. I'm not supposed to plug 1 into this piece, but I have to. Am I going to start from this point? Am I going to start from this point? Am I going to start from some other point? When we plug 1 in, we get out 2. We're going to start from this open circle right here. The slope is down 1 over 1, and then I stop. If I plug 2 into this function, I get out 1, but it's an open circle. This function is not defined anywhere at x equals 2. So I have open circles on both the endpoints. This function is not continuous at the endpoint of 0 and the endpoint of 2. Because the left endpoint, the right-hand limit does not equal the value of the function. So it does not have continuity at x equals 0. And for the right endpoint, the left-hand limit does not equal the value of the function. Therefore, we do not have continuity at 2. So let's do these questions. F at 1 does not exist. Okay? And we're looking for which one is not true. This is not true. F at 1 exists. It's right there. It just doesn't equal the value of the limit. Let's check the rest of them out just to make sure. The limit as x approaches 0 from the right exists. Yeah, it exists. It's 0. The limit as x approaches 2 from the left exists. Yep, it's 1. The limit as x approaches 1 exists. A lot of people think that this is false. It's true. The left-hand limit is 2. The right-hand limit is 2. Therefore, the limit as x approaches 1 is 2. It exists, and the value is 2. The limit as x approaches 1 of f of x does not equal f at 1. That is true. The left-hand limit, the right-hand limit are both 2. Therefore, the limit as x approaches 1 is 2. Yet f at 1 is 1. It is a removable discontinuity. 59. Which of the following points of discontinuity is not removable? If I cancel all of these, I can cancel 2 of the x minus 3's with 2 down here. I still get an x minus 3. I can cancel all of the x plus 1 because they're squared. I can cancel 2 on top with 2 on the bottom. I can cancel all of these. I can cancel the x's. But I can only cancel 1 of the x minus 2, so I'm left with this. If I cancel all of the repeated factors, these would be removable discontinuities. X equals 0 is a removable because the factor that created this x equals 0 canceled in both the numerator and the denominator. X equals 1 is removable. All of the factors of x minus 1 canceled. This cancels. So we have a removable discontinuity. But at x minus 3, it is not removable. At x equals 3, I should say. At x equals 3, we have a vertical asymptote. And that's an infinite discontinuity. Every factor in the numerator has to cancel with every common factor in the denominator for that factor to produce a removable discontinuity. X equals 2, by the way, is still an x-intercept. It's an x-intercept in this particular problem. It's still defined by this function that's left. But the one that is not removable is x equals 3 because it's an infinite discontinuity.